Hello everyone. In this video, I'm going to discuss a tiling question. So suppose that we are given an A by B grid and we are trying to find out the necessary and sufficient condition such that it would make it possible to fully cover this entire A by B grid using 1 by M and N by 1 strips. So just to give an example here, consider a 3 by 4 grid here, and suppose that the subgrids throughout, I'm going to call these two subgrids, and suppose that we are given 2 by 1 and 1 by 2 subgrids. And the question is, can we tile this 3 by 4 grid using these two subgrids? And the answer is yes, we can do it this way, for example. Notice that the question is not asking us about the number of ways we could do it. It's just whether it's possible or not. Just a simple example that shows us that it's not always possible. Just consider 3 by 4 again. But this time, suppose that I'm given 2 by 1 and 1 by 3. And let's try if I could actually tile this 3 by 4 using these two subgrids. So 2 by 1, then 1 by 3, 1 by 3. Then down here, I'm basically stuck. This part, I'm basically stuck. I don't know how to tile it using 1 by 3 and 2 by 1. I cannot use 2 by 1, of course, and 1 by 3. Once I place one of them here, then I'm gonna be like left with one square that is not covered. So this is an example that shows that it's not always possible. You can try different ways and just convince yourself that this is really the case. I cannot cover a 3 by 4 grid using 2 by 1 and 1 by 3 subgrids. Okay, the question is asking about necessary and sufficient condition, right? So let me give you a sufficient condition right away. It's simple and it's easy to guess. So sufficient condition. What's sufficient? Sufficient is watch this. If either M divides B or N divides A, then the A by B grid and A by B grid can be fully covered using 1 by M and N by 1 strips. Okay, so why that's the case? The reason, proof of this. Suppose, for example, that M divides B, then M, then B is equal M times K for some natural number K. By natural number, I mean K is 1, 2, 3, or 4, etc. So K is a natural number. Then do this. Then this is the grid that we have, right? This is A by B. And I know that B is equal to MK, so I'm gonna do this. 1M, 2M till Km. So basically I'm going to cover the A by B grid row by row using the 1 by M subgrids. And that basically gives a covering. So this is one situation. The other situation is where I have my grid and I know that n divides A. So here let's assume that A is n times t for some natural number t. And here we do the same, but instead of row-wise, we cover the entire grid column by column. And that gives a full covering, right? It's true that I didn't use the horizontal subgrid that I had, but the question is really not asking you about the number of it. It's just whether we could cover or not. If n divides A, yes, we could cover the grid using the two strips that we are given, even though we are just using one of them. Okay, now I'm going to claim something very interesting, that the condition above is also necessary. This means that if an A by B grid is fully covered using 1 by M and n by 1 strips, then either M divides B or N divides A. So this is basically what we want to show, and this is the hardest part of the question. Okay, so how do we do the proof of this? The proof goes by way of a neat trick, which needs some definition from calculus. This is a definition of an nth root of unity. Is a complex number z such that the following holds. Z to the power n is equal to 1, and z to, and if, let me, where is this? And if z to the power a is equal to 1, then n divides a. This part is important. This is basically telling us n is the smallest number to the power of which n is the smallest number that such that z to the power n is equal to 1. If we have any other number such as a, that z to the power a is equal to 1, then n must divide a, right? And you can see that the other way around is also true. This is a if and only if condition. The other way is trivial. Like, this basically means that z to the power a is equal to 1 if and only if n divides a. This is what it means. Okay, and assuming n is larger than 1, this identity also holds, right? And the proof of this is why? This is because Zn minus 1, which is equal to this, is 0. And I know that n is not 1, so the smallest number such that z to the power that number is equal to 1 is not 1, is larger than 1. So that basically means that this is not 0. Then I must have this part equal to 0. And so we have this identity as well here. Okay, sounds good. Now, how exactly this is going to help me to show the claim I made here about the necessary condition? Let's go back to the grid we had again, right? This is an A by B grid that we have, A by B. And so it has A rows and B columns. So, and so we have A times B squares here, right? Square. And inside each square, I'm going to write a value. And that value is Zn to the power. Suppose that this is row I, column J. And that value is Zn to the power I, Zm to the power J. Zn to the power I times Zn to the power J. What's Zn? Zn is an nth root of unity, and Zn is an mth root of unity. Okay, so these roots of unity exist and they satisfy the property that told you, I just told you. Okay, sounds good. And now what? So I have the grid and I'm writing like complex values inside each square. And the first question is, what is the total sum of of the A by B values that we have? What's the total sum of all these A B values, A times B values? And the answer to that is we're gonna see in a second. So let's do this. Sum of values, just the first row. Row number one. Row number one is Zn times, all of them have a factor of Zn, which I can factor out actually. Zn to the power B, right? And let's do the same for the second row. Sum of values, row number two, it's Zn to the power 2, then the same factor as first row. And I can repeat this, repeating till sum of values, row number A, and this is Zm to the power A times the same factor as all the other A minus 1 rows. Okay, and so I'm gonna do a total here. I'm gonna write total and sum all of them. Total sum is equal to Zn times Zm plus Zm b minus 1, then 1 Zn a minus 1. And this is equal to Zn times Zm times fraction here, Zm to the power b minus 1, Zn to the power a minus 1, divided by Zm minus 1, Zn minus 1. Okay, sounds good. So I managed to find this total sum here. It's this value that I have here. And now assume that, suppose that we have actually covered the entire grid using 1 by m. So suppose, suppose we have covered the entire grid, the entire A by B grid using 1 by m and n by 1 subgrids. So something interesting is going to happen here, and that is that therefore thus sum of the total sum that we have computed here, thus total sum is equal to what? Is equal to sum of values for subgrid number, let's say I, for I from 1 to t. So basically I'm assuming that I have covered the entire A by B grid that I have here. This is the A by B grid, and I use like I subgrids. I use T subgrids, and covering the entire uh, A by B grid that I have here. Okay, and this is obvious why, because it's like doing this summation in two different ways. One of them is just going square by square. The other one is just looking at each subgrid that I have and sum the values, and then sum the values of all the uh, values I get, the like subsum I get from each subgrid. Okay, so this is a simple observation, but there is a simple catch here that these values are all equal to 0. That basically means if I pick any grid here, any subgrid here, and sum the values inside, I must get 0, even if it's vertical or horizontal. I would get the value 0 if I sum like the values written inside each of this. And so the proof of that claim is proof. Let me write the claim first. Claim sum of values inside each subgrid is equal to 0. And I'm gonna give a proof of this in a second. Why? Suppose it's vertical, for example, like case 1, case 1, vertical subgrid. So I'm given a vertical subgrid here, and suppose that, let's say this is this one, and suppose that this is row P, column Q. So the value written inside is Zn to the power P, Zm to the power Q. And the value in the next cell, let's say it's Zn to the power P plus 1, Zm to the power Q. And so on and so on, right? I have this, and I have Zn to the power P plus n minus 1, Zm to the power Q. Let me actually make this one a bit larger. There you go. Okay, now I'm gonna do the entire sum here. Of course, I can factor out zn to the power p, zm to the power q. Then I get zn plus zn to the power n minus 1. But I know that this factor here is 0, so the entire sum is 0. Done. So vertical strips, subgrids, I get 0. You can do case 2 is also similar for horizontal. Case 2, horizontal, similar to case 1. Similar to case 1. Sounds good? Okay, so what's the conclusion? The conclusion is that this sum that we have calculated here must be also 0. So therefore, Zn times Zm times Zn to the power a minus 1 times Zn to the power b minus 1 divided by Zn minus 1, Zm minus 1 is equal to 0. And this basically means that either Zn to the power a is 1 or Zm to the power of b is 1. And this basically means by definition of roots of unity that n divides a or m divides b. And that completes the proof. Thank you for watching.